Backlund transformation, or in abbreviation it is called BT. Backlund transformation was initiated long back. Actually, it is initiated in 1880s, but since the nonlinear differential equations developed after 1950, so it has a tremendous application now. এখন এটা খুব application আছে তো actually BT may be of two types: auto BT or hetero BT. Auto Backlund transformation and hetero Backlund transformation, which creates a relationship between either the same PD or relationship between solutions of two different PDs. But actually DT, that is Darboux transformation, and BT, Backlund transformation, both serve the same purpose. What is the purpose? Starting from a trivial solution, they are moving towards non-trivial solutions. That's the interesting thing. So let us see how it defined. Suppose let us consider the two partial differential equations. Both by the dependent variable are u and b for those. So equation 1, 1, 2, you show the equation. This partial differential equation, it's a equation of u, and equation 1, 1, 3 is b. So if we consider the following pair of relationship, bi u, x, ut, etc., and v, vx, etc. equal to 0 between u and b and their derivatives. If bi equal to 0 is integrable for v, then this particular expression and the resulting v is a solution of g, capital G, equal to 0. Then the relation bi equal to 0 is an auto Backlund transformation. The simplest example of Backlund transformation is well-known Cauchy-Riemann condition in complex analysis. For the analyticity of a complex function f u plus iv, that is ux equal to vy and ux equal to vt, ut equal to minus vx. Suppose we consider the Laplace equation, both in u and v. These are the Cauchy-Riemann conditions: ux equal to vt, ut equal to minus vx. So suppose we consider the simplest equation, vxt equal to xt. Then according to a second solution of equation 117 and 118, u has to satisfy del u del x equal to x and del u del t equal to minus t. So the solution is given by u equal to half x square minus t square. Suppose we consider with complicated equation, a sine Gordon equation. Del 2u del x del t equal to sine u, but u is a function of x and t. So let us consider these two relationships, 1, 2, 1, 2, 0 and 1, 2, 1. Half del u del t plus del v del t equal to alpha sine u minus v by 2, and half del u del x minus del v del x equal to half 1 by alpha sine u plus v by 2 between u and v. Here we may consider another equation for v also of the same type of 119. So if we differentiate 1 to 0 with respect to t and 1 to 1 with respect to x, we get equation 1, 1, 2 and 1 to 3. Now using this simple relationship, del 2u del x del t equal to del 2u del t del x, and del 2b del x del t equal to del 2b del t del x. And if we add 1 to 2 and 1 to 3, and using these two relations, so del 2v del x del t, this is gone. Then del 2u del x del 2 equal to this plus this, which is nothing but the sine Gaussian equation. So what? Sorry, sine Gaussian equation. Yeah. So we see that u of a sine Gaussian equation. So similarly, in a similar fashion, we can show that we satisfy the sine Gaussian equation. Just instead of, if we take subtraction of the equation 1 to 2 and 1 to 3. One more equation. What is Liouville equation? Liouville equation is del 2 del x del 2 e to the power u. Similarly, we choose two equations: ux plus vx equal to root 2a to the power u minus v by 2, and ut minus vt equal to this. Just same as that of the previous case. If we take derivative and addition and subtraction, we get the equation 1 to 9. It is e to the power u. Okay. Now the important thing I am to teach you that how to find out soliton solution by using Backlund transformation. Suppose 130 is the sine Gaussian equation, and we have to find a solution using the Backlund transformation. It is seen that the auto Backlund transformation for equation 130 is defined by the following pair of coupled nonlinear partial differential equation 131 and 132. So we can easily form a known solution of equation 130. We should be able to use the transformation of equation 131 and 132 to obtain the second solution of 130. That is, what is the basis of Backlund transformation or Darboux transformation? From a very known, trivial known solution, we can find out a relatively complicated solution or non-trivial solution. Suppose we choose b equal to 0. Here u equal to 0. Sine 0 is 0. It is a solution of 130. Here b is equal to 0 is also there. So if we put v equal to 0 here, we get the equations for u. Del u del x equal to this and del u del t equal to this as 133, 134. So if del u del x equal to 2 by alpha sine u by 2, then after integration we can get the relation between u and x, where psi t is a arbitrary function. We got 135 and 136 simply by integration. But psi t is an arbitrary function, and here phi x is an arbitrary function. So after substituting, we get a relation between psi, phi, x, and t. So if we want to make compatible, we want some compatible values of psi t and phi x, then psi t will be k minus twice alpha t, and phi x will be k minus twice x by alpha, where k is an arbitrary constant. So now putting the value of phi and psi, we can get the solution as tan u by 4 equal to c to the power alpha t plus x by alpha, or u equal to 4 arctan c to the power alpha t plus this tan inverse x by alpha, or c equal to e to the power minus k by 2. So starting from zero solution, we can obtain a solution which is not so trivial, that is non-trivial solution. This is the beauty of the Backlund transformation. Similarly, we can find out the solution of Liouville's equation also. So solution of 143 may be written in the form of, since these are function of x and t, some function of x plus some function of t. These are two arbitrary functions of x and t. So v equal to 5 plus psi is the Backlund transformation of 141. So, Liouville 140. So 141 and 141 del u del x plus del phi del x. Del u del x plus del v del x. So v equal to 5 plus psi t. So it will become del u del x plus del phi del x. This is equal to this. And here del u del t, del u del x. So putting the value u plus phi minus psi minus 2 phi. Just to write in this fashion, u minus phi plus psi, we write u plus phi minus psi minus 2 phi. So because u plus phi, we need u plus phi. So if we multiply by e to the power minus u plus phi by 2 on both sides, we get right hand side root 2 e to the power minus phi minus psi by 2. So we can integrate 145 with respect to x. It's a function of x only. So u plus phi here, and e to the power u plus phi minus u plus phi is also here. So minus 2 e to the power u plus phi by 2 after integration. If just we take u plus phi to z, it can be done easily. So minus e to the power minus z by 2 dz dx type of things. So integrating, we get minus 2 become top. So minus 2 e to the power u plus phi by 2, and right hand side, this is the integration. After integrating, just easily you can get 146 or 147. Why this arbitrary function ft came as some derivative root 2 f plus t. Again, if we use the same trick to 142, here we have done for x. Now here, if we want to do it for t, that is, if we use the same trick in 142, we get the relation 148. So from 147 and 148, we can get the value of ft. You can find out the function ft as 150. So substituting the value of ft in equation 146, we put here 146 ft, we get the relationship u equal to this one, or uxt equal to this one by 151. But uxt is the solution of Liouville equation 140. So I have some meeting. আমার একটা meeting আছে. So I am to leave today. You calculate these things yourself. So I'll give you some other. আমি তোমাদেরকে আরো কিছু প্রবলেম দেব, যেটা পড়ানো হলো সেটা কিন্তু অনেকটাই পড়ানো হয়েছে, আর একটা জিনিস পড়াবো, তারপরে তোমাদেরকে প্রবলেম দেব, তোমরা কিছু প্রবলেম করবে। হ্যাঁ, এই যেগুলো আমি দিলাম এখানে অঙ্কগুলো কষে দেওয়া আছে, নিজেরা আরেকবার কষবে। ওকে, ঠিক আছে, আজকে এই পর্যন্ত। আমার এক্ষুনি মিটিং আছে, একটা মিটিং অ্যাটেন্ড করতে হবে।